So with that, we are now to our feature presentation. I'd like to introduce Eddy Zuppel and Dean MacNeil from the National Research Council, or the NRC. As you may know, the NRC is in the process of opening a new research facility in Winnipeg. With that, we will have local representation that will have access to all that the NRC does nationally. The question is how do we know when and if we should contact them? Dave Fraser of the NRC is a matchmaker between industry and companies who may benefit from the NRC capabilities. If you'd like to be introduced to Dave, please contact me or today's presenter, Eddy or Dean, and we'll be pleased to get you in contact with Dave for a conversation. So our presenters today, Eddy Zuppel is currently the program leader of the Clean and Energy Efficient Transportation Program. He oversees research and development activities aimed at assisting industry and policy development in the low carbon mobility sector. He manages over 50 projects in the area of aerodynamics, alternative fuel applications, batteries, electrical machines, fleet energy efficiency, and hydrogen applications. He joined the NRC in 2015 as a senior project manager, following 11 years in the transportation industry, where he held different managerial positions, including section chief of a multidisciplinary team of 20 engineers. Dean MacNeil studied under the supervision of Dr. Jeff Don at Dalhousie University for his PhD in chemistry in 2001. This was followed by his employment at Gillette Advanced Research Center, the Duracell division, investigating new advanced alkaline and lithium consumer batteries, and a postdoc fellowship at the University of Toronto with Ted Sargent on quantum dot solar cells. In 2007, Dean was awarded the NSERC FOSTEC Industrial Research Chair at the Université de Montréal, and since 2010, he has been employed at the National Research Council of Canada, where he now leads a group of 12 researchers and technicians on evaluating and integrating energy storage devices within a number of environments. So with that, I pass it over to Eddy and Dean of the NRC, who are going to give us an overview of their work in battery testing and optimization.
Great, thanks, Ron. Hope everyone hears me all right. And yeah, I think, I guess what I was told about this presentation was to just try to give you guys an overview of what we do, and to show you some interesting projects we've been working on in the past, and maybe what we can work on in the future. So I'll take it from here. Eddy will jump in with a couple of slides, that sort of intro slides that describe his program. But yeah, as Ron mentioned, I'm a team leader here at National Research Council. Been in that role, I don't know, 5 years maybe. So I'm leading a bunch of younger researchers and some older technicians, and looking into various applications of batteries and energy storage devices. And so let me do the transition here. Okay, here we go. So NRC, I hope this is pretty known out there, but just in case, we do have a presence within every province and in Canada. Unfortunately, the territories don't have a research lab, but we do have what are called IRAP offices, and I suspect most of you know what IRAP is. Essentially a business interaction group that tries to, you go to them and they try to help you support some advancements in your technologies. But the research facilities are all focused on different things depending on their location, and typically it's tied with the local environment. For example, if you're in St. John's, it's got a lot of ocean research, but it doesn't always have to be the case. And we're divided into these different research centers. We have about 2,600 scientists in these 14 research centers. Mine, I'll get to that in a second, but our really three key activities are really business innovation. There's a part on federal policy mandates. Obviously, the federal government has a policy, submits a policy, and we're supposed to sort of help support that in ways we can. And then we have some basic science. There's a lot of basic science that goes on at the NRC as well. So here are the research centers. Broadly, these are the vice president areas, focused areas. Myself, I'm in the one that's highlighted in yellow. It's called Energy, Mining, and Environment. It's almost a catch-all for different things. So as a battery and energy storage, we're obviously linked to energy storage. It doesn't mean it doesn't activities don't happen in other research centers. But so, for example, Eddy is part of the automotive and surface transportation. We also work quite heavily with aerospace, looking at potential aerospace applications for energy storage, and as well as construction, who are applying energy storage devices into different construction environments. So as I mentioned before, NRC is sort of divided into these focused research programs, and they support direct activities in key areas. Now, as a battery group, we work with a lot of different these programs, and depending on who or what we're doing, they're really focused somewhere else. But the two key ones is the one Eddy will talk to next, and then but we also have the Advanced Clean Energy, which is sort of our home-based program for myself, where we're really looking at energy storage devices, low carbon fuels. So how do you produce hydrogen, for example, or how do you do bioenergy changes, zero carbon fuels. And I mentioned we're also involved heavily with the Green Aviation Initiative, as well as high performance buildings. So I'll pass it off to Eddy. He can talk about his particular program, which is very focused on the electric vehicle.
Thank you, Dean. Good afternoon, everyone, and thank you, Ron, for the opportunity to present today. As Dean mentioned, the NRC is composed of many research centers, but also several programs that span across the research centers that create a link between the various capabilities and resources and the delivery of benefits to different stakeholders. So the program that I'm responsible for, the Clean and Energy Efficient Transportation Program, focuses really on the development of clean and energy efficient technologies for industry. But we also work with other government departments such as Transport Canada, Environment Canada to help provide science-based data for policy development. So the program is split up into 6 major thrust areas, including aerodynamics, alternative fuel applications, batteries, electrical machines, fleet energy efficiency, and hydrogen applications. In each of these areas, we have researchers and facilities to support various levels of technology development. We also see in the middle a more common thrust that touches the peripheral activities. And in the center, we see that there's activity related to technology watch, life cycle analysis, and vehicle level activities focused on modeling, simulation, integration, prototyping, testing, and demonstration. We also have capabilities related to EMI, EMC, and we integrate as much as possible new types of technologies such as artificial intelligence, machine learning, cybersecurity, and data analytics. So given the focus of today's discussion, I thought it would be interesting for everyone to learn a bit more about our battery thrust and provide a little bit of context as to how Dean's team fits in. So these are the general activities that are covered or hosted within the program. And we see that with respect to batteries, we touch upon most of the value chain from the advanced processing of battery materials for different types of chemistries, mainly lithium-ion liquid electrolyte chemistries for the time being. We have battery assembly facilities and expertise, a battery prototyping line where we're capable of assembling pouch cells, both R&D size and EV size pouch cells. We can also perform similar types of assembly for smaller coin cells that are used for research and development purposes. We're currently also working on developing a new capability for the manufacturing of battery module prototypes as well. Once the actual systems are manufactured, we have a significant amount of characterization capability throughout the council, in particular in Dean's team, where we can look at the performance and durability of the various systems from the cell level all the way to the pack level. In parallel to all of this, we have battery modeling and simulation capabilities where we can model the electrochemical system, the modules, or the entire pack to understand what the thermal effects are with respect to different types of duty cycles and different types of environmental conditions. We've also in the past conducted vehicle to grid and vehicle to X assessments, both simulations and field trials. And Dean will surely get into some of those activities in his presentation as well. We are looking at supply chain development. So we started about 5 years ago at NRC an industrial R&D group called LibTech, which brings together different members of the lithium-ion battery supply chain, from battery material producers to battery cell manufacturers and battery pack integrators and vehicle OEMs. And the intent is really to try and develop the supply chain in Canada by aligning the requirements from battery manufacturers, vehicle OEMs with the specifications of the upstream suppliers. So the group currently has 6 members, 3 partners, and several enablers such as Natural Resources Canada. And the last area that is one of the main points of focus of Dean's discussion today is battery safety. So I won't get into a lot of detail there because Dean will cover most of it, but just to say that this is one of the largest areas of expertise and one of the areas where NRC is leading, a world leader, from the cell level all the way to the vehicle level. With that, if you have any questions regarding the program, not only related to batteries, related to the other thrusts, please don't hesitate to contact myself or Dave Fraser. And without further ado, I'll pass it over to Dean for his featured presentation. Thank you.
All right, thanks, guys. So as you saw, I mean, batteries are part of a lot of different activities within the council, and I kind of like this graph. I mean, I would say it's still changing all the times, but it sort of allows me to sort of show where myself and my team play within this group. So I mean, within a battery, there's a lot of active materials which have a lot of effects on the mining and how you get them and how do you process them and how do you purify them, and all that feeds into energy materials, right? Producing these materials, producing fuels, producing hydrogen. How do you get them? How do you make those materials for that? And then once you figure that out, well, then you're producing your batteries. And then how do you make those batteries relevant? Well, you start building packs and you start evaluating them, and then you have your application, right? What is it applying? So where does my team play? It's really here in this circle. We're not looking at prototype cells that some company may be developing. Usually it's not at the point where you've got the robust quality that you need for these sort of scenarios, these environments. So we allow to play it sort of at the high end of this chain, and we're really tied closely to whatever application it is. It's really fundamental for us to understand what the company or what the application will be. If it's aerospace, there is a complete different set of protocols than if it was, let's say, stationary storage. So my team, this is sort of our call to arms scenario. We have the know-how and experience to assess, integrate, and improve the operation and safety of a wide range of electrochemical energy storage. You'll see a lot of battery stuff. That's just mainly the focus now, but we had done lots of work with fuel cells in the past, and then flow batteries. And so we're not really confined to to lithium-ion batteries, but it's the hot topic for now. And we do that for industry as well as government organizations. And a lot of the government organizations don't have the knowledge of the technical knowledge or the background on these, but they're seeing wide adoption by industry. So they come to us to help them out with some certain points. So we really are committed to provide innovative testing, design, and analysis to that industry within Canada and also abroad. You'll see some of our stuff is being used worldwide, and we're having quite a bit pick up abroad. So my team itself really consists of 7 PhD scientists and engineers. That includes materials engineers, mechanical engineers, electrical engineers, chemical engineers, power engineers. So very heavily engineered focused for my staff, as well as 4 very competent technical staff. And then as part of our sort of commitment to increase the knowledge and the knowledge base of Canada, we do have off and on rotating numbers of students, usually probably about 2 a year that come through our facility for usually 4 to 8 months at a time. So one of the highlights of my team is this new building here. So this is our building that we built, our purpose-built building we built in 2018 to really test the performance as well as the safety of battery systems and battery cells and systems. And it is only my team in here. It is completely our unit. So it's just a nice picture in the wintertime we like to show pretty much at completion. There's also a YouTube video that will walk you through it and you can look at it, various things. I mean, this kind of gives you the size, these last, it's a facility, basically the central bay is where all our heat producing equipment is. And then we have these test bays along both sides of the building. And to give you an idea, they're pretty much mirror images, except that this side of the building, the east side, is actually focused for abuse testing. That's why you see all this ventilation. And but the last 2 bays can be doubled, so we can fit in full-size vehicles here and test larger systems if needed. To sort of give you an overview of what its capabilities are. So on the performance side, we can test anywhere from cells, modules, and packs from about 5 volts to about 800 volts. And we can do this a number of ways. Typically, we divide them into either do you need high precision, which would have unique testing capabilities, and then standard battery chargers. But usually the cells or the systems we test have fairly strict environmental conditions, and people are investigating them for typically those extremes. So we use a number of environmental chambers and the like, and some of those are more standard surface cooled chambers, but we do have some unique high precision environmental chambers that can go down to low temperatures, but keeping those cells at very precise temperature. Any performance testing, we typically do some tear downs to figure out why things didn't work or why it failed. We can integrate various CAN buses and SMS buses. And in particular with electric vehicles, we do a lot of battery pack removals. We do integrations of CAN bus, testing that out, simulated driving conditions. And as Eddie mentioned, we do have some vehicle to grid or vehicle to home or vehicle to X testing. And we actually have on campus a test bed to do that. So here's a picture inside showing pretty much our cells and pack testing capability. So pretty much goes from cell level here at this side here on the right to pack level testing on the left. And we also have some other cell level testing in another facility, sort of our original facility, but it's really focused on small cells. So if you know anything about batteries, there's typically 18650s. Those are the ones that we do in another lab. They're about the size of your index finger. What we do in this facility is really more the EV size batteries. So these ones would be your the ones that are about the size of a piece of paper. usually, I don't know, 1/4 of an inch to 1/2 inch, 3/4 of an inch thick, depending on the manufacturer, to these large prismatic cells, to even larger big bricks that are about 5 kilograms each, that at the cell level, that some people are employing for large energy storage units. Now, the abuse side, we do that at cell, module, pack, as well as full systems, depending on the size. We can do numerous sort of standard tests that are standard abuse tests, so nail, crush, shrapnel. We have some bullet testing capability. I mean, we had started out our whole abuse testing started out with military, and obviously a bullet test is a potential event in the military scenario that you do need to test. But it actually is a very good test for other scenarios as well. Gas emissions, we have a unique gas emission analysis. We can tell you the composition of any gases that are released, heat release rates, and in thermal runaway. I'll get into a lot of these further on. Now, nice thing about being at the National Research Council, if we don't have it, other people might have it. So there are things like vibration tech that we don't have in our facility, mainly because other people had it. So then we can tap into those other facilities across the council to do our type of testing. For example, the very large climatic chambers, if you want to put a vehicle in and test that. One thing I do like to emphasize, we do not certify battery products. You don't get a stamp of approval from NRC on your product. That's not something that we do, but we do test to a standard. So these are some of the battery standards out there. We can use those standard methods, but technically because we are a research owners organization, we prefer to use our own proven methods, or work with our clients to figure out what are you really worried about, and let's make sure we get that in your test that you're going to produce. So that's to say we have had clients also who have arranged for certification bodies to certify the products based on our testing, but we really put the onus on the client to make all those arrangements, because it's not something that we do en masse. We're not built to do that. So I mentioned some of the things that we use other facilities for. This is our fire research labs in the Construction Research Center, but here was one of the first sort of large-scale abuse testing that we were doing. So we were actually doing a fire exposure test on these EVs, but it's just an example of different things that we can grab from the council and use. So I was going to give you a little overview. So that was the performance and abuse. Some of the other things is modeling. Eddy mentioned a bit. We tend to use a Unix-based open form software to model the thermal loads or the electrochemical properties of batteries. And then in our integration, I mentioned it before, vehicle to grid. So it's just a very schematic here. I should actually change it for a real photo to show the people. But anyway, so we do have that on site. It's an interesting building that's actually designed for home automation and home energy analysis. So we've incorporated a sort of a power pad for vehicle to grid and other scenarios we can use. But I won't go into detail about these in the plan. So our clients, again, we usually use a mix of projects. We do quite a bit of private industry work where someone comes to us and asks for a specific test or a specific abuse, and we work with them. With our OGD partners, or our other government departments, or the universities, utilities, we tend to just try to feed future research, increase that knowledge. And some of the collaborations we've done in the recent times, we have international arrangements with the Joint Research Council. They're the European Union's sort of funded research organization, kind of like NRC, but in Europe. We have NHTSA, which is the National Highway Transportation Safety Association in the US, and then all the big departments, so Transport Canada, Defense Research Department of Canada, They're the research arm of the Department of Defense, NRCan, ECCC, and then as well internally. So just let me grab a glass of water. And so now I'll just kind of give you a sample, a flavor of what we do. And I'll start with the performance, and then I'll move on to safety and abuse. So this is a nice graph that really sort of fits into why performance studies are important and why thermal management in particular is important into your battery pack. So if you have your typical allowable temperature range during the operation of a battery is usually about 10 to 40 degrees, okay? And then as you increase that temperature, you start getting what's called non-uniform cell aging. So you get these side reactions that occur as you go to higher temperature. You get this different side reactions, but down at lower temperatures, right? So you're always trying to find that window is what temperature does my cell work in, and I got to keep it in that. So the thing is, there's always a delta T as you use it. These are not finite devices. As you make a cell thicker, that delta T will expand from the sides to the inside. So the question is what kind of operating window can you use, right? So the interesting story here is our first client to ask us about this. They were told by an OEM manufacturer they had to keep it to less than 2 degrees Celsius, that gradient. So the average cell temperature and the delta cell between that cell temperature. And the question was, well, what if I kept it at 3 degrees? What if I kept it at 4 degrees? How would that affect the durability of these batteries, the safety of these batteries, the cost of the batteries? For sure, the cost would go down because your thermal management would be completely different if you're allowed to be at 4 degrees than if you were at 2 degrees. So, and this is sort of another graph that shows the constant charge discharge. So as you charge and you discharge your cycle life, you do that multiple times over the full scale of its operating voltages. And you do that over different temperatures. You can see how your capacity changes, but also your cycle life sort of changes. And there's some kind of happy medium where you get your highest capacity, but at what temperature? So this is the kind of the data that supports that other graphical sort of sketch. And the trick is how do you balance those parameters? And what you do notice here too is there's a lot of scattered data. And that's important because when you test these things, their temperatures are changing all the time. So it really depends on the type of chambers that you test. And so this comes to that precision built chambers. So that comes to our precision built chambers that we developed and how we do it. And we can use it for a variety of temperature form factors. So what we're showing here is 18650. But we've actually implemented a system for large EV cells as well. And we can use them at wide temperatures. So they're good from about -30 to +60. And they offer really high precision, high accuracy, and good thermal stability, okay? So you're only changing by 0.4 degrees over 1 hour. So you tie that to high precision coulometry, which is actually measuring the electrons that go back and forth as you discharge a battery. So those things together essentially brings these numbers much tighter together, which is important to do it. But equally important is to understand what's in your cell. So this is a typical EV cell, as again, it's about the size of a piece of paper. But then inside of it are layers of cathodes, layers of anodes, and you analyze that. Thermal, very critical parameter. So we outfit them with different thermocouples, different heaters, trying to understand how heat is generated, where it's generated, and how it's dealt with within these cells. There's also lots of different chemistries. So chemistries change, those parameters change. Your operating demands, right? What power you need, what temperature you're operating at, and then your thermal configurations, right? You can have passive cooling, forced air cooling, and liquid cooling, refrigerant cooling. There's lots of other unique methods that are coming out as well. And all this affects your service life, right? So how far you're going to get, and that affects the warranty of scenarios. So we collect all that type of information. We work it in with modeling and trying to predict those sort of performance topics or lifetimes. I'm not going to go into modeling because it's not my thing. I would have to bring my modeler in here to go through it. But essentially, break it down into some fundamental physics-based equations, right? And then as we sort of build those fundamental equations up and sort of exploring sort of higher end questions, we start to make approximations to that to try to speed up that calculation. And then you sort of build up your battery packs. This is just a mix of 18650s, and you see how well you need to keep it cool to keep it at the right operating temperatures. And one thing that we do, I've pushed this since I've started the team, is to try to really validate all of these equations, make sure they're right. So we do a lot of fundamental model validation, and here's at sort of at the material level, but you can also do it at the cell level as well. You build up these meshes into cell designs, right? And then you start building approximations to those fine meshes, and you make these meshes even bigger courses, and then start building your packs. So this is a Nissan Leaf battery pack model. And then you can start generating how temperature is dealt with within that pack, right? Where is it doing? And really temperature is the key driver to durability, right? The tighter you keep that temperature, the longer that battery pack will operate for the most part. And you can investigate, well, here's just an example of something you can do with the battery lifetimes. What if, here's your original approximation, okay, based on some model and some thermal management system. If you go and change that, you might improve battery life, you might decrease battery life, and you as an OEM would pick one that you feel is the best for your product or your warranty or your anything. You basically will define what that value is, right? And so here's an example, just simply changing the heat capacity or the heat transfer coefficient from a system. So if you have 7, which I think is our base case, okay, which is a passive, you get about 4.7 years. But as you start introducing more and more different types of heat transfer methods, you can get cycle life that increase over the years. So this is in years. But it's important to know that this is for one specific configuration, and it doesn't apply to everything, right? There's some of them are different models will have different results. So, so our performance side of our facility can really run from simple validation of a supplier's specs. You want to know if they last for the 500 cycles that they say they do, or to those elaborate models that I showed to you. And we can do that and build them up. We can validate battery packs. And we make sure everything is validated. And then you can use those to improve your performance, improve the durability, and then reduce costs. So I'll move over to our abuse testing studies and safety studies in general. And one of the key aspects that we have been doing over the last probably 5 years is, and this is one of the key technologies that was developed over that, is this localized rapid heating for triggering thermal runaway. Now, in about 2017, we started supporting Transport Canada on this topic for global technical regulations that are being developed for electric vehicles through the United Nations. And so one of the key researchers on my team developed this heater. And the heater is unique in that we can mold it to the size of any type of battery. So here's the planar. So these would be for your planar cells. but those cells that might be curvatures, so the 18650, we can curve it. And we use that to trigger thermal runaway rapidly. And I'll explain to you why it's important to do it rapidly as we move through these slides. But the methodology that we developed has been gaining sort of approval in the world space here, and it's being incorporated into a new ISO standard for electric vehicles called ISO 6469 as one of the methods to trigger thermal runaway in a EV system. And it's being considered for use within the global technical regulations as well. But we've been able to use this to really probe battery pack designs for numerous clients. And we're also marketing this and providing this to various research organizations as well as OEMs that do their own battery pack testing around the world. I think we've got up to 15 different organizations at the moment. So what is it actually meant to do? And this is a visual, a schematic visual of it. We ramp the cell or the heater to a certain temperature very rapidly. So if you notice, it's 5 to 15 seconds. And that's important because you want to get that heat rapidly to the cell. You don't want your system to take away that heat. It's followed by a soak phase, anywhere from 30 seconds to maybe 2 minutes. We're typically less than 30 seconds or right around 30 seconds. And then what that will do is trigger what's called thermal runaway, where exothermic decomposition reactants inside the cell are triggered, and they basically take over, cause and run out of control. Heat goes up high and the cell goes into what's thermal runaway. And in a battery system, these events do occur. It's happened in the field. You've probably seen pictures of batteries catching fire. And it's an event that will continue to happen no matter how well the manufacturing techniques improve. The thing is to make sure you reduce those frequencies, but you also need to make sure that you test your product, that it can withstand something like this, because it will happen. And so our goal is to trigger thermal runaway, and then we watch for how does that event propagate through the cell. Hopefully there's no propagation as it's propagates, sorry, through the pack or through the module or through whatever device that we have. Hopefully it stops, and that's a good result. But a lot of designs tend to just propagate one cell after another, and you got this big catastrophic event. And the importance of this technique is that conventional external heating uses a constant input power. And that means that your heat transfer to the cell is it's not efficient, okay? You're losing a lot of that heat because you're transferring it to the cell very slowly. So here we try to use thermostatic control, where we heat really rapidly to a certain temperature and then just pulse it with power. And that eliminates element burnout, or what we call sidewall ruptures, which are actually heating the cell too much and putting a hole through the cell. And it minimizes the energy required to trigger a thermal runaway. So I'll go through this. This is the heater. I know we got about 10 minutes left, so I should be able to get through this in time. So here's the heater on a module. I'll tell you the module, it's actually a Tesla Model S, because you'll see it in the next picture. An 18650, we apply a little heat transfer paste, insulate it, so we make sure the heat is going to the cell and nowhere else. And then we test it in this module. So these are, in the Tesla Model S, there's at least 6, typically 8 of these modules in a battery pack. And then we trigger thermal runaway in one, and we see what happens. The other unique thing about a Tesla system is that it actually is liquid cooled. And what that means is there's a liquid that passes along every cell, passes pretty much between cells to keep it cool and keep it, well, not cool, keep it at the right operating temperatures. These liquid cooled systems are difficult to test at the module level because they tend to, any heating source, they tend to wick heat away. So our method was really able to show how you could still trigger thermal runaway in these liquid cooled systems. And that has a big effect on the results of the test. Because if you run the test without liquid cooling here on the left, and you compare it to a cell with a test with liquid cooling, you'll get, as you'll see in a moment, very different results. So the heater is identified here. This is the IR sort of from the top. And as soon as I push play here, the thermal runaway should happen very rapidly, and then we'll watch. Although I need to switch back to, okay, here we go. So this should show up. So they're fairly much synchronized in time. You can already see the difference that liquid cooling and without liquid cooling has on the visuals here. But even on the IR, you see the without liquid cooling, much higher temperature, maximum temperatures here, much lower when the liquid is running. Now, we're not surprised that the cell entered thermal runaway. That's what it's designed to do. What we're looking for is how does that propagate through the pack? Does it propagate? How many cells does it propagate to? Does it propagate to all of them? And what does it do? And so I'll move it quickly through here. I won't play the whole thing, but essentially the results occurred. The final results was that without liquid cooling, that initial thermal runaway event, so here you've seen a second one here, propagated to its 4 nearest neighbors, okay? It stopped after that point. But the one that had the liquid cooling going through did not propagate at all. Okay, so it stopped at that one cell, which is the result that you're hoping for. Now, that's not the end, right? There's a big difference between doing a test at the module level than applying it to the vehicle level. And so the question was, and all the OEMs would ask us as you're trying to introduce a new testing methodology is, can you test this in a fully operational vehicle, okay? This is a very tough scenario. A lot of the original battery testing standards cannot test in an operating vehicle. For example, nail testing, it's not very easy to do that test at the operating vehicle. So we tend to try to use as much as possible the same setup pack level, and we just really minimize instrumentation. We make it so that the heater is invisible to the full system. So when you turn the car on, it doesn't detect that you've modified the pack slightly. And then to even push it even further, we tend to put the test in a driving mode. So we actually turn the wheels, get it going to show that it can be done. It doesn't have to be run in a driving mode. It's just showing that it can be done. And the big point that I'm trying to make before is that there is a big difference between module and pack tests, right? So a module and pack tests really have no containment, right? Your pack might be self-contained, but you don't have that vehicle architecture over, and those will have significant differences in the outcomes of the test, right? Because you don't have those thermal barriers, those masses. You lose a lot of discharge energy from the system, right? And you don't have easy access to oxygen in a vehicle level test. So here's a different pack architecture just to show you the differences. This is actually from a Nissan Leaf. So we install our heaters. We put them in 2 locations, mainly to make sure if something doesn't go wrong, we don't have to redo this. So here you install the heater right through here. We cut away a little bit access to the cells. We go through it. So I'll go through the video quickly. Essentially, the battery pack is outlined here in blue. You'll see the driving wheels move as soon as I start to play. And this is our indicator is when we're heating and when we're not. You might see the red light. It's difficult, I know. The heater is actually located roughly about here. And what you'll see eventually is that the pack will rupture here. I'm not sure if I play it long enough here, but you'll see other things happen. We'll start this. So I think it starts within about 5 seconds. We'll start the heater, but as you see, we have started the the wheels moving. And what we're trying to see is, does the car detect that there's a problem and shut off? Right? What kind of errors does it give off? So there you go. So the initial event, you start seeing smoke emanate from the battery pack. And that continues for a bit. I'll go through the results. So here's the services. It's basically that appeared right after we initiated heater. You get these service EV system appearing on the dashboard, so that it does alert the driver. So within 11 seconds from starting our heating on our heater, we have triggered thermal runaway. 1 second after that, you could see the gases come out of the seals from the battery pack. We turned off heating at about 15 seconds, so within 4 seconds. So there's now no more energy applied to the system. So within at 18 seconds since the start of heating, roughly 7 seconds after thermal runaway, that's when we see the visual dash warnings to the driver. There's also slowly brought to a stop, mainly because it was suspended. It'd be the same thing on the road. And then slowly the gases start building up, and then roughly about 40 seconds in, there's a significant amount of gas. I will show you sort of that position here. This is the test itself with outside view. So you can see that through this, there's a significant amount of gas being released, smoke, but no fire. There may be a fire inside the battery pack, but there's no visual fire outside. And it actually continued over about 12 minutes. So 12 minutes after we had started heating, there was finally an external fire from that rupture site that we showed. Essentially, the material breakdown happened. Oxygen was allowed from the outside, was allowed to get in, and the fire started. At the point, once the fire started, the hazardous environment within the vehicle was detected, right? And that's basically based on sort of meters that we put within the vehicle. But up to that point, if the driver had the windows all sealed up like they were, it was fine. And after about 2 minutes after that, the firefighters on site came in and applied water to the test. So in terms of a summary, the heating approach I showed to you really has been adapted to about 10 to 15 our battery pack design. So RESS is rechargeable electrical energy storage system design. So, and we typically get those from Transport Canada. Pretty much every electric vehicle popular electric vehicle you see in Canada has been tested in our labs. And then many more by our other partners around the world. And it's been demonstrated to be reliable, very repeatable at all levels of testing. So cell, module, pack, and vehicle. And the neat thing is we don't have to disable any components. We don't have to, that could influence safety. And as I mentioned, we supply this to OEMs around the globe. And we tend to, when we do these for private companies, we really work closely with you guys to make sure we're doing what you really want, and we're going to give you an answer that you really are after. So in general, my team really has quite a bit of experience on testing batteries in different environments and in answering your concerns about performance or safety. And we look forward to testing all these different new energy storage technologies that are trying to be deployed. So obviously, I don't do a lot of this work. I wish I did, but this is my team members who are very keen on it. And over here, this is Julio, one of our more experienced technicians. He's now in his outfit for COVID, so everyone has to don this whole sort of get up nowadays with COVID, but he's ready to help work with you guys. So that's about it. I think I'm right on time. I'll stop there.
Oh, thanks so much, Dean and Eddy. That was really good. If anybody has questions, please feel free to submit them on the Q&A feature on Zoom. Just to start us off, One of the things, getting back to some of your battery aging testing, one of the things that I know myself, if I'm looking at buying an electric vehicle, range anxiety is one of these things. And you factor in the fact that, you're going to buy the vehicle new, you're probably going to own it for 5 years or 7 years. So the battery life the battery range, will degrade over time. And then on top of that, you have the cold weather here in Manitoba, right? So it can get to -30, -40. So my performance is going to decrease as well. And one of the things that's happening, and you talk to the folks that are in the bus market, is because there's so much range anxiety, they're basically putting batteries in just about every spot they possibly can, and they're carrying around all this weight just in case. So in your mind, or in your research, not in your mind, in your research, what have you learned through the testing that you've done that might quell some people's range anxiety, or is it real?
Yeah, so I'll privy this question by the disclaimer: I own an electric vehicle. I have over the last 6-7 years. So some of that is biased towards my experience with my own personal vehicle. But I wouldn't say that. I would totally agree that people are buying bigger batteries than they probably need. What also actually was killing, and then this is even in my own vehicle, was killing the battery range more so than dragging around a battery that weighs probably twice as much as I need, is you actually charge it all the time. Every time you got home, when you first get these cars, because of that range anxiety, you're charging it all the time. So you're staying at high states of charge, which are actually the most detrimental, even over temperature changes, which are more detrimental to the state of health of that battery. So as you get more familiar with it, you start saying, well, wait a minute, tomorrow I'm only going 20 Ks. I don't need to charge this to 100%, right? And I think those are things that come with experience. As a I know you guys are focused sort of heavy duties, and it's hard because the people that are buying these and the transit authorities or other heavy duty users are typically unfamiliar with actually using an electric vehicle. So then they suffer from that range anxiety more so than the people that are used to driving it and knowing how to deal with it, right? So it's a lot of perception. In testing, you see that. We do a lot of testing, whereas if maybe you use the same total amount of energy, but instead of doing it constantly, you do these spikes back and forth. In a vehicle, you can't really do, but in our test phase, we can. And you can see that over time, the loss of batteries capacity is different than if you just are constantly going back and forth. And a lot of it has to do with those high states of charge and low states of charge, but more so high states of charge, just staying away from them.
Yeah, and if you look at a typical fleet, they'd be out running during the day. And if they come back at 70% charged and they're constantly cycling between 100% and 70% charged, you're basically, from what I understand you're saying, is you're actually aging your batteries faster by doing these small charge cycles than you would if you were to run it 2 or 3 days on a charge and then charge it again.
Yeah, and that's where, I mean, I didn't get into it, but the vehicle to grid scenarios could actually be beneficial to the vehicle users, even though everyone thinks it'll actually cause more usage on my battery and more degradation on my battery. But yeah, they're using your battery, but they're using it at times when you're not using it. So it actually is dropping the state of charge and getting you out of those danger zones, right? So you actually may see better durability because it's being used in those vehicle to grid scenarios. And fleet operators are the perfect example of it, right? On the weekends, I guess your lower power demands on weekends anyways, but overnight they could cycle those things and then be ready to go in the next day. They know exactly what route they're going. They know they have to be at 50% or whatever, and they just keep it at 50% at the end of the day for 6 a.m. or whatever.
Oh, very interesting. Very interesting. So based on the research that your team has done, if you were building a heavy vehicle that was battery electric, what would be the top 3 design considerations that come to top of mind to you that we should have at the forefront when we're thinking about battery location, battery enclosure, battery cooling, mitigating events and those sorts of things. What advice would you have?
So, yeah, I would say thermal management is the key, the top one, right? How do you efficiently thermally manage these large battery packs, right? Making sure that your cell selection matches your thermal management strategy.
Mm-hmm.
A lot of people don't think that you can just swip and swap, and it doesn't. It's not the case, and so that's key. Making sure you understand your route, right? If it's a delivery van, it's a completely different scenario than a long range transport.
Mm-hmm.
And I guess charging, and it's, if you're doing it extremely fast, or if you're doing it relatively fast, or you're just using it throughout the day, how do you manage that, right? And if you have availability of extremely fast charging, well, maybe you'll go for a lower battery pack. Maybe your expectation on battery life is lower, and you can accept things that happen when you charge fast versus charging slower. So to me, those are the three things.
Interesting. So one of the questions that comes through from Nestor is, has anyone studied the potential for fire risk in depot charging situations where multiple fleet vehicles are charged indoors simultaneously in a single location? Okay,
so the fire risk from one vehicle to the next, is that?
Yep.
Yeah. It's a. Actually, I saw a video this morning just about that topic, and I've seen pictures in China where electric buses all line up on the end, and you can see from one bus and end to end, and the fire propagates to the next bus, to the next bus, to the next bus, to the next bus, right? I think it's a legitimate concern. It is important that these events are still very rare. But it is something that you need to try to mitigate. Hopefully it's mitigated so that it doesn't propagate to the next event. It usually doesn't happen through charging. You're not going to have multiple scenarios through charging. That's not how it would happen. It would be one bad actor, maybe on charging, maybe not. And then that bad actor causes the event to occur in sort of the neighbor vehicle. But really, perhaps there's ways to build firewalls between the buses within your designs. But yeah, the event I saw this morning was in Stuttgart, where the whole bus depot went down because one electric bus had a problem, thermal problem. It's still investigating the root cause, but yeah.
It's almost like we need autonomous technologies to have all the other buses to scram when one decides to have an event.
Yeah, I mean, I think that will exist eventually. And I mean, yeah, and it was funny because the fire department, they came in with their hoses, but in the end, they ended up using snowmaking cannons to make sure everything is cool, which is a neat concept. And that's something that we've been trying to implement in our own lab, but not at that scale, but yeah.
So is it true that when a fire like this erupts, that after you put it out, there's enough thermal energy there that it can reignite? And sometimes it takes 2 or 3 efforts to finally get the temperature below critical so that things stabilize? Is that a true scenario?
Yeah, it's true. A lot of cases, not that they don't reignite. I mean, the battery packs are sealed, right? So they're very difficult to tell if they actually are extinguished, right?
Mm-hmm.
So that's one aspect. Some of them are never really that extinguished. But yeah, that's what happens. Firefighters on light duty vehicles have different takes on this, on how to deal with it. Europe, they tend to bring open containers filled with water, and they actually take the car and drop it into the container to deal with these fires. I'm not sure how insurance agents like that, but that's one aspect, one way to do it. Others have shown these things reigniting 2-3 times in depot yards. So
That's great. Thank you. So there's been quite a conversation going on between Yizheng and Eddy on some basic chemistry level batteries. One of the things that is being asked is NRC done any research in the past on NAS batteries?
Yeah, so that would be not really in Eddy's wheelhouse. That would be more in my research center's wheelhouse, because NAS batteries, sodium sulfur, are typically used for large energy storage systems. So we have done, let's say, paper studies on it, official sort of in-lab, sort of test lab scenarios. I don't think we've done much. But there have been a number of paper studies and understanding the technologies. I can definitely link you to the right person to talk to you about it. But experimentally, we haven't done a lot of work, at least in the long past. Sodium sulfur have been around for a long time. In sort of the 70s and 80s and 90s, I think there was some fundamental research going on about them, but nothing in the recent. But let me reach out to me, and then I'll link you with the right person to talk to you about what we've, at least the paper studies on those.
That's great. So when you read publications and those sorts of things about future battery technology, solid state batteries and those kinds of things, what excites you of what you see in the future? What, if you consider that on heavy vehicles, because we have so much mass to move, we need these massive batteries. And by having lighter batteries means, it's one of these things, the lighter the batteries are, the farther we can go. The lighter the batteries continue to be, the further we can go, the less structure we need, which lightens the vehicle, the further we can go. So there's almost like a snowball running downhill sort of thing. If we can get the energy storage to a point where it is lighter, it allows us to do a bunch of things that is important for large vehicles. So when you look out into the 5-10 year future, what technologies out there excite you?
I'll let Eddy probably address some of that, because I'm not sure I'm so much excited as I am about, oh boy, how are they going to fix that? Because there are a couple big issues that these new chemistries need to solve. I don't think lithium ion is going away anytime soon. You will get new and improved cathodes that'll give you incremental improvements. You'll still see quite a bit of engineering developments, right? Just these larger cells that people are producing is an engineering development. And when you put it into a system, make big advances. And I think any, let's say, large scale displacement of lithium ion technology will be quite a ways away. I'm not sure it's 5 years, I would say 10. But the two biggest things that I worry about in that are probably really important for the heavy duty is charge rates. These new technologies are not necessarily going to be easily charged very fast. Maybe for a station to station, if you have a big enough battery or light enough to do that, okay, great, and you can charge overnight, but don't expect your long haul transfer to stop halfway and charge on these things very fast, at least as fast as a traditional lithium ion. And safety. So many of these advanced battery scenarios are focused on lithium metal or its derivatives. And to date, that is not something that is earth shattering. I mean, we've been looking on those batteries for a long time, since the 70s. And yeah, there's been developments, but it's still going to be a long road before people are safe. Let's say our systems are safe for that. But Eddy, maybe you have some more to add about that.
No, I think I agree with you, Dean. I think there are a lot of incremental improvements that are still possible with respect to the conventional lithium-ion batteries. At NRC, we're working on new cathode chemistries, but also new anode chemistries where we're trying to integrate silicone into graphite in order to increase the energy capacity. There are challenges associated with that, and we're trying to increase the content of silicone, but because of the volumetric change of the silicone, it causes problems in terms of degradation. So there are many possibilities that can increase the overall energy capacity of the conventional battery, then there are new chemistries, new solid electrolyte chemistries that, as Dean said, it's probably in terms of research and intellectual property, one of the biggest areas of research in industry and in academia. However, we're probably still 5 to 15 years away from serious commercialization of that technology. And I think that the main impact will be on the heavy duty sector. I think in terms of the light duty sector, we're probably already there in terms of the energy density that we need. But when we look at Class 8 tractor trailers, aerospace, marine, there's still a ways to go if we want to meet the operational requirements of various fleet operators. So I think we're still quite several years away, maybe even decades away, but there are complementary technologies such as hydrogen that may be able to bridge the gap as well.
Excellent, thank you. Thank you. Serge Boulay is asking, to support heavy vehicle in remote locations, vehicle to vehicle power transfer will be likely needed. Has this been or will it be tested?
I know there's been light duty people that have tested sort of range extenders. So they're not actually going vehicle to vehicle, but what they do is sort of tow a spare battery pack behind the key vehicle and have done it similarly. I'm not sure that's probably the way to go. I don't think, in most cases, I mean, these transport trucks are not traveling as a fleet together on the same roads. So I'm not sure how efficient that would be, but no, I haven't heard too much of that. There'd be a lot of protocols and a lot of driving, maybe with self-driving trucks or something, that platoon, maybe that's a scenario where your truck in front would be losing a lot more power than the trucks in back, and maybe they can perpetuate, but that'll be a long ways off.
Yeah, I kind of see this question maybe being ice road truckers or somebody that, they're out in the middle of nowhere and they're dead and they got to get going, is to be able to swing an umbilical cord from one live vehicle to another to limp it to where it's got to go or something like that.
Yeah. Yeah, I think the usage case is probably minimal compared to the other issues that need to be solved.
Okay, interesting. Yai Xing is mentioning that most of the batteries in China are lead acid in the buses. So he had mentioned a fire event in China that potentially could have been a lead acid battery fire, I would think, or a bus fire that propagated from bus to bus and maybe didn't have much to do with the batteries, possibly.
It could be. I mean, a lot of the original high press light duty vehicle tests was due to the lead acid when they go into sort of submerged scenarios, they do cause the fire, and it has nothing to do with the high voltage. The high voltage, once it caught fire, extenuated the circumstances. But yeah, there's a lot of sources of fire. The picture I saw in China, I mean, you can debate whether whether it's a real picture or not, I guess, right? So I don't know enough about the scenarios, but sitting on these global let's say roundtables, there's enough of these events out there that people are concerned.
Yeah. Concerned enough about garaging a personal vehicle, or is the likelihood of an event pretty much the same as having a problem with your gasoline vehicle?
Well, I think Tesla's done a good job to show that it's not the same. It's a very much lower potential.
Yeah.
But again, when you have a GM Bolt recall that says Bolt owners don't park 50 feet close please park 50 feet away from your nearest structure, vehicles, garages, and everything. I mean, those are serious warnings that make it very inconvenient for a user. So.
Well, like with any technology, it's going to evolve and it's going to become safer and safer and safer, right? So
Yeah. So, but I mean, like I said, I've had mine for 6, 7 years, and I park it in the garage all winter long. So summertime, my kids need the space for the bikes and stuff, so it stays outside.
Well, with you being a scientist and being comfortable putting your car in the garage, it should give a lot of us comfort. So that's good.
Yeah, we did test my car out on as a real slide. Not my car, but my model out there. And yeah, let's say I was very attentive to what the results would be.
That's good. Question for you on battery recycling. I noticed that on one of your first slides in your deck is efforts that the NRC has been involved in regards to battery recycling. And if you consider transit buses, highway buses, basically anything heavy duty, the thinking currently is that the battery packs will probably have to be replaced midlife, a bus lasts 18 years, replace the battery packs at 9 years in order to get another 9 usable years of life out of the batteries. Now, there is going to become a huge waste stream of batteries as a part of this, and with Priuses and Leafs and those kinds of things going through battery changes. What's the NRC's involvement been in the recycling of used batteries?
I'll let Eddy answer that one. He knows there's a lot of involvement, but Eddy can probably summarize it pretty well.
We're currently working on a project where we're funded by Natural Resources Canada to look at hydrometallurgical processes to extract the valuable materials from batteries, in particular lithium, nickel, manganese, and putting it back into the supply stream for the production of new batteries. So we're trying to support different recyclers such as LI Cycle or Lithion, who have actually already created partnerships with various vehicle OEMs such as GM and I believe Hyundai as well. Right now, the biggest challenge is that they actually have the production facilities, the prototyping facilities, the pilot lines in place, but there's a lack of supply in order to justify the business case. But as you said, in 5-10 years, there will be a tsunami of batteries that will need to be either repurposed, reconditioned, or recycled, depending on the application and depending on the state of health of the battery when it reaches its end of life. So this is actually an area where there's still quite a bit of research and opportunity because there are only a few companies that are in that space, but there will likely need to be many more in order to meet all of the demand.
Yeah, I know there's an effort. The World Manufacturing Forum was part of an effort bringing Audi, Volkswagen, and a lot of the large vehicle manufacturers together to study this whole idea of what are we going to do with all these batteries once they're past their useful life. And I know it's something of concern to an awful lot of automotive OEMs.
Yeah, one of the things for sure, I mean, there's too much value in them to let them. So I have no qualms that these will be 100% recycled, just like our lead acid of today. And actually, what's unique too is you go to Japan, if you buy an electric vehicle in Japan, you actually don't own the battery. You own the vehicle, but you don't own the battery. So you actually have the manufacturers are actually liable to take the battery back at the end of the life of the car. So maybe I'm not sure how that would apply in North America, but it's an interesting concept.
Great. I've got time for 2 more questions here. This one's from Paul Canton from New Flyer. How do you see hydrogen fuel cell technologies integrate and to some degree displace some of the larger energy demand applications that battery electric is struggling to completely satisfy?
I'll let Eddy take that. I have views on hydrogens that don't always follow the government mandate, let's say, on hydrogen at the moment.
Well, I think, and I know that Dean probably has the same opinion, but hydrogen does have its place, especially in the heavy duty sector. When we're talking, as I mentioned before, Class 8 tractor trailers with heavy payload requirements, certain aerospace applications, marine applications, off-road applications such as perhaps mining. There are, however, several challenges with hydrogen, starting with the energy efficiency of the entire supply chain, from the production of clean hydrogen to the use of a fuel cell. Compared to a battery electric vehicle where you can probably have a 90% energy efficiency from start to finish, hydrogen, you're probably looking at 40% or so. So there are significant losses. Fueling infrastructure also remains a major challenge, especially in the heavy duty sector. Even though we have fueling stations for light duty vehicles, the requirements for high rate fueling of, for example, locomotives or aerospace applications still has certain technological hurdles. For example, the expansion of the hydrogen at the nozzle causing significant temperature changes. Those are still technological issues that have to be addressed. And of course, there's the kind of the elephant in the room, which is the availability of green hydrogen. So right now, 95% or more of hydrogen is produced using steam methane reforming, which generates CO2. So if we want a zero emission solution, we need green hydrogen, which has to be produced using electrolysis. So there's a cost associated with that and a lot of technological development. So I think that, due to the high energy density of hydrogen compared to current batteries, it has a place. However, there's a lot of development and investment that has to be put in place for it to become a viable solution.
Thank you. Okay, last question. Has the NRC looked into wireless charging for vehicles as an up-and-coming technology? I'm aware of an effort in Sweden where they actually have charging strips embedded in the road that are energized as a car goes along. It'll energize a 1 meter piece as the car travels. And they report that for every mile the car travels on the road, they can get another 2 miles off of a charged road, so to speak. Interesting, like if you're operating a fleet, having your charging system in the ground is better than hanging all this stuff from the rafters of your buildings and those kinds of things, but also creates issues. Is there anything that the NRC is looked at in this area?
So I think we're well aware of the technology. I don't know if we've actually had projects focused on those topics, sort of more so than just talking about them. So maybe Eddy's aware if we've had specific projects.
I think we just started looking at a feasibility study for that exact type of situation. And at the end of the day, I think it comes down to the total cost of ownership, the cost of operation of the entire system throughout its lifetime. Mm-hmm. You have to consider the operational requirements and compare it to, for example, having individual charging stations. The operator at the end does not want a more costly solution. They want an emissions-free solution that costs the same or less than what is conventionally available. So I think that's the bottom line. And that's why with these clean technology, it really is right now a case-by-case assessment. There is no, I guess, catch-all answer or catch-all technology that can address everyone's problems.
Well, that's great. With that, we're reaching the bottom of the hour. And as promised, we're going to end here at 3:30. I'd like to thank Eddy and Dean for presenting to us today on the NRC's efforts on battery technology. Earlier in the webinar, Dave Fraser had shared his email address. If you have any questions of the NRC and to find out if they can possibly help you on your journey to zero emissions, feel free to reach out to Dave, and he'll be pleased to get back to you and help you out. With that, thank you very much for attending. We appreciate you being a part of this webinar series, and we look forward to seeing you again in future webinars. Thanks so much.
See you guys. Thanks.
Thank you.